finish up with this. How many chemically different hydrogens do we have? Four. That OCH3, CH3 is not a CH3. Oh, you know, there's a difference here. Everything matters in the immediate chemical environment. That's what makes these hydrogens resonate at different frequencies. So, superficially, I'm expecting 4 resonances. I say superficially because I can have spin-spin splitting, which will make a resonance be not a single line, but a multiplet. So if I had a quartet, for instance, that would be described as one resonance because the signal from one hydrogen is just split into 4 lines because of some spin-spin splitting with neighboring hydrogens. So, in terms of spin-spin splitting, well, you can see the area ratio is 3 to 2 to 1 to 3. Obviously, is how the areas are going to come out for the 4 resonances. And you could assume that if hydrogens are chemically different, you will see a different resonance. You get a little crowded sometimes. Things do overlap, but you should generally assume that. So, will the A hydrogen be a singlet or a quartet or a triplet or whatever? Singlet, because it doesn't have any chemically different neighboring hydrogens. It's going to be a 3 hydrogen singlet. What about B? Doublet, because it's split by the 1 chemically different C hydrogen. So that's a 2 hydrogen doublet. What about C? A 1 hydrogen triplet. And what about D? 3 hydrogen singlet. Doesn't have any chemically different neighboring hydrogens. Now, the issue of where these peaks will be in the spectrum, I've saved for last because it's not super important. Most of the power of NMR does not come from where the peaks are. It comes from the areas underneath the peaks and the spin-spin splitting or lack of spin-spin splitting. So I'm going to see for this peak, wherever it appears, a 3 hydrogen singlet.
To go up and right like it used to go up like
That means, of course, that that's a CH3. What are the odds that it's not a CH3, but it's 3 equivalent hydrogens attached to different carbons? That's just not probable. So I'm assuming it's a CH3, and whatever it's attached to doesn't have any, there's a wall, a firewall here. There are no chemically different neighboring hydrogens. And the same thing over here, I've got a CH3 with no chemically different neighboring hydrogens. Right here, where I'm seeing a doublet and a triplet, that means that that chunk, and the 2 hydrogens, is CH2. That's your assumption. Now, it could be 2 hydrogens on 2 different carbons that are chemically equivalent. That's more likely than 3, but still assume 2 hydrogens is a CH2. And the fact that it's a doublet means it has 1 chemically different neighboring hydrogen, reinforced by that hydrogen showing up as a triplet. So that's a 2-carbon chunk that I've identified, And then I've got two methyls that can't have any neighboring hydrogens. The last piece will be where these resonances appear will clue you in a little bit to what kinds of hydrogens are present. But bear in mind, you will not see any direct evidence of oxygen. You will not see any direct evidence of chlorine either. You will infer their presence from how they affect where the peaks appear in the spectrum. All right, let's stop there.
No. So we use my binoculars.